In this video, I'll show how to build and run a hydrodynamic simulation of an offshore floating wind turbine. All starts by sizing the hull in a spreadsheet. Then, we use Ansys Spaceclaim to design the 3D model. Finally, in Ansys Aqwa, I'll show the configuration of the model properties, with mooring system and a catenary power cable. We'll see some results like response amplitude operators, and wave diffraction radiation animation. A good example of offshore wind turbine for this work is Equinus Highwind, which consists on a spar type of hull. This website presents some useful information, like the substructure, mooring system, hull size, masses, and more. Before starting, let's understand a bit more of spars. The spar platforms have three generations: the classic, the truss and the cell spar. The lower part of the hull consists of a heavy or fixed ballast, followed by a flooded section and a variable ballast section. In the classic and truss spars, the variable ballast is near the hard tanks. But in the cell spar, the variable ballast is part of the flooded section. The hard tanks are the upper part of the hull. Many patents and development of the spar concept was done by Edward Horton. This concept is very stable for installations in hurricane-affected areas like the Gulf of Mexico, or in heavy weather conditions like in the North Sea. They are also more safe against damage or operation mistakes than the other types of hulls, like the semi-submersibles. Let's start by sketching the structure. At the bottom we have a fixed ballast. Above it there's a flooded section tank for the variable ballast. At top of hull are the hard tanks. Main parts of wind turbine are the tower, the nacelle, the hub, and the blades. The hull external diameter, total length, freeboard, and draft are needed. The freeboard is the length above sea level and draft is the length below the sea level. Porosity is a simple way to estimate the inner volume available for the ballast. This is a fraction of the external diameter which is lost due to the shell thickness and other structural reinforcements not known at this stage. Displacement of the hull is the volume of water displaced by the submerged structure. This is what will produce buoyancy capacity for the hull. And its center is the center of buoyancy. To estimate the stability of the floating hull, we need to determine the overall centers of buoyancy and of gravity. In a spar hull, the center of buoyancy is always above the center of gravity. That's why this concept is unconditionally stable. In other words, it is conceptually impossible to capsize. I have added a coordinate system, where z is pointing upwards. Also added symbols to make clear the center of buoyancy needs to be above the center of gravity. Fixed ballast is made of a heavy density material, such as magnetite. A reasonable density for this is 5,000 kilos per cubic meter. You can find this property in marine construction related company websites. As this volume is internal, the inner equivalent diameter is used to calculate its mass. The center of gravity and the mass moment of inertias are needed to model the rigid body later in Ansys Aqwa. Mass moments of inertia equations can be found in Wikipedia. We need the horizontal axis and longitudinal axis inertias as well. The variable ballast is made of seawater, as it is an open tank to the ocean. The level of ballast is controlled by pumping compressed air to the top of the tank. Again, the mass, the center of gravity and the inertias are needed. I'm adding the internal area now, as it makes easier to calculate the rest. To calculate the mass of the hull, let's use a simple approach of mass per unit length, of 10,000 kilos per meter. Let's add 5 bulkheads to the hull, each one weighing 80 tons. The secondary steel, which is the mass of internals, piping, ladders, accessories for mooring and etc., will have an additional mass of 10 tons per meter as well. If we add all this, the total mass of the hull is coming as 2,400 tons. But, how do we know if this is reasonable? We can check by using information from Highwind. Searching more, we can find a brochure with more information, length, diameter, and mass of 2,300 tons. As our hull has same general size as the Highwind, we can say we have a good estimative. Last structure to add is the topside, or, in this case, the wind turbine. A 5 MW nominal power wind turbine is being considered, with a hub height of 100 meters. Let's estimate the mass of the nacelle as 150 tons, and the rotor mass as 80 tons. Total top components mass will be 230 tons. The top component's center of mass will be the same as hub height. The inertia of the nacelle can be simplified as a brick with 2 meters wide, 3 meters high and around 5 or 6 meters long, with distributed mass. Let's ignore the hub inertia and the blades as well. They are very flexible and may not contribute much. To consider blades it would be also much more complicated as their properties depend on pitch angle. We now need a mass summary, to be used to determine the global center of gravity. It seems I forgot the tower in the top components. Let me add a tower with 7.5 meters, and the height enough to have the hub height at 100 meters, discounting the freeboard of the hull and the nacelle to tower top distance, of about 2 meters. Let's take the same tower mass from the reference, of 670 tons. In the summary, we add all masses, centers of gravity, and calculate the moment each part creates around the origin of the system. The origin is the sea level. The global center of gravity will be the sum of moments divided by the total mass. So, now we have both centers of buoyancy and of gravity calculated. To have the structure in equilibrium, we still need to determine the correct level or mass of variable ballast. We know the buoyancy capacity of the hull. We also know the total mass. The net balance of mass must be 0, so the structure buoyancy is equal to its total mass. To find this, we manage the variable ballast. Let's use Excel Goal Seek tool to target the net mass to 0, by changing the variable ballast height. That's it, we have about 30 meters of seawater ballast to have the platform in static equilibrium. A spar stability is a simple calculation of the distance between centers of buoyancy and gravity. The BG length should be always positive, and the higher it is, the more stiff the structure is against overturning moments, or in other words, stronger against the forces of the environment, like waves, wind, and current. If you need more stability, you can increase the draft, the diameter, and play with the fixed ballast as well. But, a reasonable ratio between cost and benefit must be considered. Last step is to add mooring lines, and a power cable. They will not affect wave diffraction and radiation calculations, but are needed if you simulate in time domain. Let's define the water depth as 1000 meters, and 3 mooring lines only, to make it simple. The mooring lines are attached to the hull at the fair leads, which can be 50 or 40% of the hull draft. Let's assume an angle of 45 degrees to the vertical axis, for a taut leg mooring system type. We need to calculate the coordinates of fair leads and anchors for adding them later in the model. Deep-water offshore platforms can use a mixture of chain and polyester lines. There's a short chain section at top and another at bottom of the line, and the polyester line is in between. The polyester is much less stiff than the chain, thus it adds elasticity to the mooring system, but reduces the total mooring weight. The top tension defined at installation of the platform can be 15% fraction of the line breaking strength. We need to define some properties for the chain, the polyester line, and the power cable. As an example, searching for offshore mooring lines, we can find Intermoor website. Their offshore mooring page has chain data sheets, from where we can choose the diameter, and have other properties like the maximum breaking loads. From the same manufacturer, we can find polyester line properties. Ideally, the poly line need to have equivalent breaking load as the chain. We are using here lines with around 200 mm diameter. The chain equivalent diameter is about 2 times the chain nominal diameter. The polyester rope can absorb some water, so the equivalent diameter is less than the nominal. We can use around 75% of its original diameter. This is to compensate for the correct buoyancy of the line, which Ansys will calculate. Axial stiffness and breaking load are needed to estimate the line stretching and the top tension. Now, the amount of axial deformation of the poly line can be estimated. To target for the top tension in Ansys model, we need to compensate for the deformed length. As the deformed line will be longer after tension is applied, we deduct the stretched length from the total. I've made a mistake of inserting the stiffness in kilonewtons. All units here are in Newton meters. We finally see the stretched length is about 15 meters, for a line of more than a kilometer long. The power cable can be attached to the bottom of the hull. This line will be in catenary shape, but let's assume 45 degrees top angle to estimate its length. Touch point in seafloor will need to be adjusted manually in Ansys later to make it simpler for now. The sum of vertical forces is a nice to have. As the weight of the lines is not being considered in the platform net mass and in the ballast level calculations. This vertical force can be added to the mass summary if you want to have a correct freeboard for the platform in the time domain simulation. Mooring fair leads, anchor points, cable hanging point and touch point, need coordinates to be used for Ansys model. It's just a matter of calculating the X and Y projections of the lines. Now, let's start the CAD model. In Ansys Workbench project, include a hydrodynamic diffraction system and a time response system. To start the CAD design, right-click Geometry and edit in Spaceclaim. In Spaceclaim, close the initial sketch and start a new one choosing the Z-axis as normal. Draw a circle with the diameter of the hull of 15 meters, or 15,000 millimeters. Use the pull tool to extrude the hull downwards with 85 meters of draft. Delete the top surface as we don't need it. Use pull tool again, without merge, and extrude up with hull freeboard of 15 meters. Use the fill tool to close the top with a surface. Verify that the hull bottom has a surface, because we need a closed volume for the submerged part. To build the tower, start a circle on a sketch on the top surface with the tower diameter of 7.5 meters. Use pull tool again and extrude to a total tower height of 83 meters. If you want a conical top section, you can reduce the total height on 20 meters. Select top of tower, add 2 planes. Now, move one plane 20 meters upwards. Sketch on the upper plane another circle with a smaller diameter, like 4 meters. Use the blend tool, select both circles and a conical section is built. You can change the height where the conical section starts using the move tool. Let's delete the inner tower bottom surface, as we don't need it. Use pull with chamfer tool to improve the hull freeboard shape. You can add a plane on water level for visibility. Now, let's sketch the nacelle on top of tower. Use rectangle, define it from center, and start it at one side of the tower. The nacelle can have around 5 meters wide and 10 meters long. Use pull tool and extrude outer lines to about 5 meters upwards. Delete the tower top surface as we don't need it. The wind turbine blades are complex to design. For easiness, I have imported a free GrabCAD model. You can search for wind turbine blade. I am using this rotor shared by Anthony Wyeth. It might be needed to do a cleanup or corrections in the imported CAD. After it is ready, import it in Spaceclaim, or drag and drop in the current model. Several move operations will be needed to position the rotor onto the nacelle front face center. Use the Move tool center and up to options to move it directly to a desired target easily. I'm removing additional features from the hub and from blades roots, to simplify the mesh generation task later. Delete unneeded surfaces, and double check other faces are all fine. Use split tool on the nacelle front face to make sure the hub and the nacelle share nodes on the edges. Blades tips were cut out to improve mesh operation. With the move tool centered on the hub, we can rotate the rotor for a new position. It is good to check that the surfaces of the hull have normals pointing outwards. This is to ensure that the hydrodynamic model do not fail to calculate the hull displacement. If they point inwards, the calculated volume will be negative. As an example, if you need to flip any of them, right-click and use Reverse Face Normal option. The last operation before moving to Ansys Aqwa is to use the Share Geometry tool. This allows to share nodes in between two faces from different parts. It seems I forgot to close the nacelle top. Use Fill tool and Share Geometry again. The geometry import may take several minutes. After done, verify all parts are in the hydrodynamic system. Here we can increase the domain size. Let's now add the point masses for each part of the wind turbine. Each point mass needs to have the mass, the center of gravity, and the mass inertias. These were calculated in the spreadsheet before. As this is a rigid body, by adding each part with its own point mass properties, Ansys will take care of the global combined mass and inertia of the structure. I've typed one wrong mass and need to correct it. If the bottom of a spar hull is flat, it offers a large hydrodynamic drag in the vertical direction. To account for the additional heave motion damping caused by the viscous fluid drag, let's add a drag disc to the bottom of the hull. Hydrodynamic drag coefficient of a flat circular disc normal to the fluid flow can be found in hydrodynamics books. Let's use for this example a coefficient of 10, which is a high number because it is for a laminar flow. Mooring lines and power cable need connection points. Let's add connections to the hull. 3 mooring lines will be connected at the coordinates calculated in the spreadsheet. The elevation of the connection is the same as the chain fair lead, which we estimated to be at about 40% of the hull draft. Last connection is for the power cable. This one can be set at the hull bottom, where it is usually the case in deep water offshore structures. We also need to create connection points at the seafloor. They are the mooring lines anchors. Again, use the coordinates calculated in spreadsheet. Power cable needs a fixed point on the bottom too. The mooring lines and power cable need physical and mechanical properties. We want to add catenary type of lines. Add the chain properties as calculated from spreadsheet. We are considering the dry linear mass. The buoyancy will be calculated by Ansys using the equivalent diameter. In the case of polyester line, the equivalent diameter is less than the outer diameter, as it absorbs some water. The power cable data is the last one needed. Let's add nonlinear catenary cables. They are connected between fixed point on seafloor and the structure. These deep water mooring lines have short chain lines at bottom and at top. The middle section is the polyester line. Use the calculated initial length of polyester as it is going to stretch by self-weight. This mooring line system is called taut leg, which has all its length under tension and no section resting on the seafloor. In this case, the anchors need to hold vertical loads as well. The power cable will be resting on the seafloor, thus the touch point is far from the fixed point. A fine mesh may be needed to detail some of the faces in the freeboard, tower, and top components. Let's use small defeaturing value and maximum element size. Check that the mesh in the submerged hull is correct everywhere to provide a closed volume which will be used to calculate the hydrostatic displacement. The elements above water are not important. We added top structure only for visualization, not for actual calculation. In analysis settings, we can set the number of CPUs used to solve the model. Full QTF matrix is set as default. It gives more precise results, including the second-order terms like the slow drift forces. Other output options may be needed if you are going to make more complete post-processing. Structure selection is useful when you have multiple floating bodies. Wave directions can be reduced to only 3, to reduce a bit the solution effort. Wave frequencies are set by automatically. Let's try as it is. Let's include results for hydrostatics. And add pressure and motion animation results. You can select the frequency to be visualized, and increase the wave height. Change result type to phase angle to see the animation for a complete wave period. Let's also include two response amplitude operators, RAO, for heave motion, which is in global z-axis, and for pitch motion, which is global rotation in x-axis. We can adjust them later after solution is done. Let's try to solve the model. Trying to solve is giving an error. The highest frequency requires a smaller element size than those we have. To solve this, let's change the frequency inputs to manual settings and limit the range. Let's use a range from 60 to 30 seconds with just a few points, as this range is far from the structure response. Set another range of periods from 30 to 5 seconds. This is the range of more interest where the structure will respond to waves. Less than 5 seconds is not of interest as they are very small waves and will not move the structure anyway. If we adjust the interval, we can get 1s period steps, which is good enough. With this limit, we avoid the solver error. Solve again and it should work. The solve may take dozens of minutes, depending on hardware. After solve, we should check if the hydrostatic parameters calculated are matching with those planned. Here is the solution for global center of gravity. Here we can see that the actual and the equivalent volumetric displacements are very close. This means the displaced volume from the mesh is matching with the equivalent displacement from total mass of model. Finally, the distance from center of gravity to the center of buoyancy is given. And we can see from the calculated metacentric height that the contribution from water plane area is very small compared to the BG. So, it's okay to ignore it for this simple spart hull design. If we check these numbers in the spreadsheet we used to design the structure, we'll see they are matching very well. This means we made a good job. Let's check the response using the pressure and motion result. The selected frequency is too low right now, which gives a very long wave with 60 seconds of period. Let's check the response amplitude operators and see what are the resonance frequencies in heave and in pitch degrees of freedom. Heave peak response, in Z direction, is happening at 0.05263 Hz. And pitch rotation is peaking at 0.04167 Hz. Let's use these resonant frequencies and update the motion animation results for both degrees of freedom. Now we can see the linear wave diffraction solution of the structure's motion at resonance frequencies. These motions look terrible for the structure. But this is only linear solution. Mooring lines and viscous drag are not yet included, and both will damp the motion. Moreover, the resonant frequencies of 19 seconds for heave, and 24 seconds for pitch are high, and most likely, not the same periods of storm wave conditions for most locations. Ideally, the system resonant frequency is designed to not match the wave frequency that causes most damage to the structure. Let's see a smaller wave diffraction of 5 seconds period. If we change the contour type to wave elevation, it's easier to see the incident wave and the diffracted wave on the spar hull. You can also select what wave component to see. If we remove the incident wave, we will see the diffracted wave from the hull structure and the radiated wave from the hull motion. The hull is not moving at this frequency, so these are all diffracted waves. Let's now run a time domain response. First, we should calculate the static stability of the system. This will help to check the platform condition, including the weight of the mooring lines and power cable. We'll use default settings for the analysis. We need to add at least one wave as input. Let's add a very small irregular wave. We do not want to cause disturbance on the water. We just want to check the static equilibrium. Let's add results for the structure's position. And also add animation results. And finally solve the model. The solution for position can be changed to the global vertical axis. We see that the platform sank some meters due to the mooring and the cable forces. The animation of the motion shows the platform is moving downwards and slightly to the side. It can be due to the wave being not so small and is drifting the hull. There's also possibility of some imprecision in the mooring design and horizontal forces caused by the power cable. Let's add a result for total force from mooring lines only. Here we have the total vertical force from cables on the structure. This is what is increasing the draft of the platform. We can see that the force reduces as the platform sinks along the iteration steps. Ansys total vertical force is lower than that estimated in spreadsheet. Main reason is the power cable top tension was wrongly calculated as taut leg, and the total free hanging length is also wrong. If we use hydrostatic stiffness of the hull and the distance it has sunk, we can compensate for this force difference in draft by removing variable ballast mass. We did not add wind or current drag force coefficients for the structure below and above water. But this can be added in geometry. You need to know the drag properties for the components and add these properties separately as needed. Now we know if the platform is stable. Let's add another time domain response by dragging it into the solution of the last system. Let's simulate an irregular wave response with a duration of at least 300 seconds for a demonstration. Other solution controls can be set here, as for example the full QTF matrix and some frequency. These are to include second-order terms and are needed for more precise calculations of slow drift effects on the floating structure. We can now include many analysis items, like forces, cable winch actions, cable failure, and irregular wave groups. Let's keep it simple and include an irregular wave modeled with Jones swap parameters. Let's control manually all the wave parameters. Let's also change wave range definition from frequency to period. To model some kind of storm wave, let's use a wave spectra with a peak period of 16 seconds, as an example. The gamma factor, start and finish periods are needed. We can see the wave spectra created has maximum energy at the peak period in this table. Let's now include wave elevation results. Include the animation. Include statistics for the structure position, for vertical heave motion and pitch inclination angles. Here, we can request forces results for the structure. We can also get the results for mooring lines or any other connection attached to the structure. Let's, for example, ask for mooring line tension forces, which is useful as you want to know if the line will survive the storm. Run the solution for the hydrodynamic system. We can now check the wave elevation to confirm the wave amplitude is coming as desired. We can see about 6 meters of amplitude were obtained during the 300 seconds of simulation. We can now check the animation. Unfortunately, Ansys Workbench only shows the structure animation, but not the incident waves in time domain. To see incident wave you can use another Ansys software package called Aqwa. We can now check the statistics of mean and standard deviation results for heave and pitch. This may be important to confirm that platform's hull design and mooring system design is acceptable. Let's include graphic results for the structure motion on heave, and also for pitch. We can see the pitch motion is about 1.5 degrees plus or minus, which is small. For the simulation time we asked of 300 seconds, or 5 minutes, the structure is still behaving very well with a storm of 6 meters height and 16 seconds period. Let's now increase the storm energy and make it happen at the structure's resonance frequency. We can see from diffraction analysis, the response in heave happens at around 19 seconds and the pitch response happens at 24 seconds. Let's use this in the irregular wave inputs. Let's change wave period to 24 seconds, and significant wave height to 10 meters. This will for sure cause severe response of the offshore wind turbine. We can confirm wave height is now much bigger and at least one wave with about 10 meters of amplitude happened at around 200 seconds time. Platform heave motion looks in resonance and is moving more than the waves, with about 20 meter total heave amplitude. Pitch inclination has also increased and about 9 degrees plus and minus is occurring after 200 seconds. The animation at exactly 200 seconds will show a large motion for this heavy storm condition. Other results can be checked, like the statistics, and the mooring cable forces. We can see that the designed mooring line top tension of about 2000 kilonewtons is now suffering a lot in the dynamic storm condition. And, this concludes this video. We have started from a sketch, making realistic assumptions to design a spar hull and a typical wind turbine. We calculated the hull size and its static stability, and the mooring lines and a power cable property. Using this spreadsheet, we then made the structure's CAD model and set up the hydrodynamic diffraction system. Finally, we ran a time domain solution with a heavy storm wave height and period, at exactly the structure's resonance response, just for demonstration, but also a bit for fun. Hope this is useful for Ansys Aqwa beginners. Good luck.